Hi, today we will be talking about the mole ratio. Okay, that is the last important point, the basic point that we need to know about stoichiometry. Okay, we actually know about this, learned about this in grade 10. Okay, so first of all, I'm going to talk about some basics, and then after that, how do we use mole ratio when we do chemical calculations, and then some specific examples as it is indicated in the examination guideline and the CAPS document. And when we look at the content today, as you can see, we don't have mole ratio here, okay, not mentioned here, but for for example, percentage yield, when we talk about percentage purity, and then any kind of stoichiometric calculations on a balanced equation, and when we talk about limiting reagent, we all use mole ratio. That's the basic thing that we need to know about mole ratio, okay? And then another point here is we are going to use the percentage composition. First of all, I'm going to show you how to calculate percentage composition, as you know from grade 10, a quick revision. And then from that, we are going to try to find out in one example. Unfortunately, time is limited. And then in one example, I'm going to show you how to find empirical formula from percentage composition, and from empirical formula, molecular formula by using the molar mass of a compound. Okay, and then after that we will talk about one example of limiting reagent, after that percentage yield, and then one example of percentage purity. Okay. Let's look at percentage composition. Actually, this is what we call as a there's a whole piece, and then this piece is composed of parts, and each part is how many percent of the whole piece. So, but this percentage composition in mass, okay? So when we talk about a compound, the mass of whole compound is 100%, and the mass of one element in this compound is how many percent of the total mass of the compound, okay? That's the question today. And determine the percentage composition of an element. I'm going to show you its basic percentage calculation. That's what we use in maths. Okay, you already know about this. What is percentage composition? The percentage composition is the mass of each atom present. Each atom, for example, for H2O, water, and what are the atoms inside? Oxygen and hydrogen, we talk about. In a compound, H2O, expressed as percentage of total mass of the compound. So which means that if the total mass of water, as you all know, that it is 18 grams, okay, because it's 2 hydrogen, 2 times 1 plus 16, we did it before, and that's equal to 18 grams per mole. 1 mole of water is 18 grams, okay, and in this 1 mole of water, then how many grams of oxygen we have? 16. How many grams of hydrogen? We have 2. So this 2 grams is how many percentage of 18? If 18 grams is 100%, 2 grams of hydrogen is how many percentage of that mass? And 16 grams is how many percentage of that mass? And then you can write down an equation like this. Percentage of oxygen, okay, is equal to mass of oxygen and divided by total mass of the compound times 100, okay? So the mass of oxygen in the water, okay, 1 mole of water is 16 grams, divided by 1 mole of water is 18 grams, times 100 is going to give us 88.89%, if you use your calculator. And the second example is the other element or atom present in the compound, what we call as water now, and the percentage of hydrogen in mass is equal to mass of hydrogen, okay? So we have 2 hydrogen atoms and each one is 1 gram. So it's going to be 2 times 1, 2 grams. So 2 grams divided by 18 times 100 is going to give us 11.11%. And if you add them up, you are supposed to get 100%. Sometimes when we have the percentage composition, whole percentage composition for compound, when you add them up, you get 99 point something, or you get more than 100, very close to 100. So which means we do rounding. As you can see, these numbers are rounded, okay? So we do rounding, that's why there might be difference if you add them up, but it's supposed to be 100, that's what we are expecting, okay? And for example, we know this methane, okay, it's a gas. Methane is a gas. That's what we find in natural gas, okay, it's a flammable gas. When we look at the CH4 and how many grams in percentage is carbon, how many grams, okay, in percentage is hydrogen. If this one totally is 100%, how many percent is hydrogen, and how many percent is carbon. And then if you look at here, the percentage of carbon is equal to mass of carbon divided by total mass of the compound. So mass of carbon is 12, total mass is 12 plus 4, as you all know that if you look at your periodic table, you can find 16, and 12 divided by 16 times 100 will give us 75%. It's a perfect number. We get a perfect number here, okay? There's no decimal places after this. And then percentage of hydrogen in mass in the CH4 is going to be equal to 4, the mass of hydrogen atoms, divided by total mass of CH4, 16 times 100 is going to give us 25%. And if you add them up, you are going to see that it's going to give us 100%. That's equal to the mass of CH4. And what is empirical formula? We know this from before. An empirical formula is the simplest whole number ratio of atoms in a compound, okay? And then determine the empirical formula for a given substance from percentage composition. We know how to find the percentage composition. We just discussed that we have 75% of carbon and 25% of hydrogen. That's the percentage composition of CH4. We have 88.89% of oxygen plus 11.11% of hydrogen, and that's what we call as the percentage composition of water. So if it is given like this, what is the empirical formula of a molecule containing 65.5% carbon, 5.5% hydrogen, 29.0% oxygen? And then by using this, we are going to find empirical formula. You know this, okay? So which means that, and if I add a molecule containing 65.5% plus 5.5% plus 29%, it's supposed to give 100% mass of CXHYOZ. I just wanted to give you an idea. So which means that X, Y, Z is unknown numbers, and then we are looking for those numbers. If I can find them, and I can write down the empirical formula. And I just said that the simplest whole ratio number, okay, sometimes it can be equal to the original formula. That's what we call as molecular formula. There's something called molecular formula of a compound. It gives you the actual number of elements. But this is empirical formula, gives you the simplest ratio between the whole number ratio between the elements, okay? So for example, we gave example of H2O2. H2O2 is hydrogen peroxide, and then you have 2 hydrogen, 2 oxygen. That is the molecular formula. And if you find the empirical formula of that, if you simplify 2 and 2 in H2O2, you get H1O1. So H1O1 in hydrogen peroxide is empirical formula, and H2O2 is the molecular formula. What about H2O? When we look at H2O, already the simplest ratio between hydrogen and oxygen, 2 and 1. You cannot simplify into a whole number, okay? Simpler whole numbers. So which means that H2O is the empirical formula of water. At the same time, it is the molecular formula. So molecular and empirical formula will be same, or molecular formula will be a bigger numbers, and the empirical formula will be the simplest whole number and ratio of it, okay? So how do we do this? I did it in the form of table to make it easier to understand, okay? If you look at this table, you know that this table is in the Google Classroom. I share this slides, so you can look at those slides when you are looking at this video. And then when we talk about 100% total mass, so how many percent of carbon we have? 65.5, given in the question. 5.5% hydrogen, 29% oxygen. Instead of saying 100%, we say 100 grams. And then you have this, a bag of this, okay, molecule. It's in the bag, okay, molecule. And we don't know how many grams. I just take from this bag 100 grams, okay? Just measure it, 100 gram sample. And then in this 100 gram sample, how many grams of this sample only composed of this compound will be carbon? If the 100% mass, and in 100% mass, we have 65.5% carbon. So which means that in 100 grams, we will have 65.5 grams. In 100 gram sample, we have 5.5 grams. In 100 grams, we will have 29 grams of oxygen. And the next step is the normal mass mole calculation, okay? So if you remember, we are trying to convert now the mass of each element or atom into the number of moles. So how do we do that mass number of moles relationship? Number of moles is equal to sample mass divided by molar mass. If I use this formula for each, okay, it's very simple. So what is the mass of the sample? 65.5 divided by what is the mass of one carbon? 12, okay? So it's 5.46 moles. And then when I look at the hydrogen, it's very easy. Number of moles is equal to sample mass is 5.5 grams divided by 1, and it's going to be equal to 5.5 moles. When I look at the oxygen, number of moles is equal to 29 divided by 16. Okay, 16 is the mass of oxygen, and then that's going to give us 1.81 moles. Okay, and then what we do is the next step is we simplify all with the smallest mole numbers. Okay, when I look at this 5.46, 5.5, 5.5, 1.81, which one is the smallest number? 1.81. What do I do is that I take these mole numbers and divide each one with the smallest one, 1.81. So 5.46 divided by 181, 5.5 divided by 181, and then 181 divided by 1.81, and then that's going to give us 1, and this one is going to give us 3.04. Okay, so you just, if it is very close to 3, we just round it to 3. And if it is, because we are using a different periodic tables, sometimes we get examples from internet, and what happens is that they are using some other periodic tables with decimal numbers. Okay, so to be able to eliminate that, we just round it. It's very close. As you can see, 3.02 is very close to 3. So you just round it whole numbers. Okay, and then what we get here is that we have how many carbon? 3 carbon. How many hydrogen? 3 hydrogen. How many oxygen? 1 oxygen. And then if you put them together, that's what we get is the empirical formula. Okay, that's what we get is the empirical formula. Sorry. Okay, there is a simple mistake here. I just want to, okay, that's what we call as empirical formula. Okay, that's what we call as empirical formula. So what is our next step? Okay, what is our next step is C3H3O1. But is it the simplest number, or is it the correct number that we are looking for when we want to find the actual number of atoms in the compound? Okay, when we look at the molecular formula, what was the molecular formula? Represents the actual number of each element, not the whole number ratio of elements in the compound, and determine the molecular formula from empirical formula and molar mass. So they have to give us, or we have to know before we go into this step, we have to know the empirical formula. What's our empirical formula? If the molar mass of the compound C3H3O1, okay? In the previous example, what is the empirical formula? C3H3O1, okay? And is 110 grams per mole. What is the molecular formula? So they have to give us empirical formula and molar mass. So in this case, what do I need to do? I just put it in the steps for you to be able to understand easily, okay? So the steps are not in order. Okay, this is number 3, supposed to be 3. Okay, so when I look at the first step, we need to find the mass of empirical formula. You know how to find the mass of a formula. So we need to find the mass of C3H3O1, that's all. Find the ratio between molar mass and empirical formula mass, and the ratio is equal to bigger one, okay? Molecular formula mass divided by smaller one, empirical formula mass. That's what we are expecting, because this is the simplest ratio formula, okay? And by using this ratio, multiply each subscript, okay? Subscripts are 3, 3, 1, but in the empirical formula with the ratio. If you find 2, you multiply each one 2 with 2. If you find 3, you multiply each one with 3. If it is 1, ratio is 1, so the empirical formula is equal to molecular formula. Okay, let's look at the same example. So in the first step, what did I do is I calculated the mass of empirical formula. Okay, that's going to be 3 carbon, 3 hydrogen, 3 oxygen, 3 times 12 plus 3 times 1 times 16. That's going to give us 55 grams per mole. And then what did they give us? They give us the molecular formula mass. That's what we call as the mass, molar mass. Okay, it's the same mass. Okay, that's 110 divided by empirical formula mass, which we just found it, 55. That's going to give us the ratio is equal to 2. And then what we need to do, you need to take this empirical formula and then multiply by 2 each subscript. 3 times 2, 3 times 2, 1 times, it gives you C6H6O2. So sometimes we have a question like this: why the carbon is first, hydrogen is second, oxygen is last one? So if you put it in any order, it's still fine, okay? For example, O2, C6H6, that's also fine, okay? But I know from organic chemistry, that's what you are going to see in grade 12. So it's always in C, H, and O in this order. But you don't have to write in this order, okay? It's up to you. So which means that our molecular formula is C6H6O2, our empirical formula is C3H3O1. This is the actual number of elements, and this is the ratio between them. How do you find the ratio between them? Divided by 2, it's going to give you 3, 3, 1. And what about mole ratio? Okay, that is the next step, is the mole ratio. Okay, I always give you this example, simple example. Let's work on the simple example. Hydrogen gas and oxygen gas goes into reaction to produce the water molecules. Okay, in gas form, for example, it's an unbalanced equation, and then what do I need to do is, by using the coefficients and numbers on each formula, in front of each formula in the chemical equation, we discussed that. Okay, so I write 2 here, 1 here, 2 here. I solve that. On the left hand side I have 4 hydrogens, on the right hand side 4 hydrogens, on the left hand side 2 oxygen, on the right hand side 2 oxygen. This is a balanced equation. So by using these numbers 2, 1, 2, that's what we call mole ratio. So which means that if I have 2 moles of hydrogen gas goes into reaction with 1 mole of oxygen gas, that's going to produce 2 moles of water molecules. Okay, so in one example, for example, they told you you put 6 moles of hydrogen gas. How many moles of oxygen gas do you need? You need 3 moles. How do I know? The ratio between hydrogen and oxygen is 2 to 1. If it is 2, this one is half. So 6 divided by 2, 3. And how many moles of water molecules will be produced if you have 6 moles of hydrogen gas going into reaction with enough amount of oxygen, or 3 moles of oxygen gas? And then we know that that's 6. Why? Because the ratio between the hydrogen gas and the water is 2 and 2. So if it is 6, it's going to be 6. Another example, we also said that, if you remember in the previous classes, we said that the mole ratio is equal to volume ratio at STP, at standard temperature and pressure, 0 degrees Celsius plus 1 atmospheric pressure. So in these conditions, the gases, okay, as you can see, all of them are gas, okay. So if you have 2 decimeter cube of hydrogen gas goes into reaction, I need 1 decimeter cube. Can you see the ratio 2, 1, 2, 1, okay? The mole ratio becomes volume ratio at STP. You can use this. And then it's going to produce 2 decimeter cube of water molecules, okay? So that is what we call mole ratio. So how can I use this mole ratio in a one simple long example, okay? Imagine that, I always give you this example, if 100 grams of hydrogen gas goes into reaction completely. So which means that we also have oxygen, more than enough oxygen. So if I need, for example, 50 grams, I don't know, we are going to calculate now, 50 grams of oxygen, I have 50 grams of oxygen, or I have 60, 70, 80, more than enough, okay? So that's how the 100 grams of hydrogen gas can go into reaction completely. And then that's going to produce us, okay, H2O molecules, okay? So if 100 grams of hydrogen gas goes into reaction completely, A, how many mole of hydrogen gas goes into reaction? So I want to find out 100 grams of hydrogen gas is how many moles? B, how many moles of oxygen gas needed for the reaction? I need to find out by using mole ratio. I need to find out, because I just calculated the number of moles of hydrogen gas. I need to find out how many moles of oxygen gas do we need, and then from that one, how many grams of oxygen will be used. So this one, how many moles of oxygen needed should be converted into mass, and then from that we can use again mole ratio between H2 and H2O, how many mole of water will be produced, and how much volume of water molecules will be produced at STP. So as you know that all of them are in gas phase. And then how do we solve this question? Okay, how many mole of hydrogen gas into reaction? 100 grams is the sample mass and is equal to sample mass over molar mass. And we know that the hydrogen gas is H2, okay? 2 times 1. I'm not using these when I calculate molar mass. This is molar mass, 1 mole of H2, okay? This is 2 moles. No, you don't use this when you find this capital M, okay? Only the formula for capital M, molar mass. 2 times 1. 2 grams per mole, 100 divided by 2 is going to be equal to 50 moles of hydrogen gas. It's easy calculation, you can do it yourself. And the next